we asked the question, said, what would you guys like to see? And a few of you said electrical. So we came up with a seminar on basic electrical theory. All right? Now, the electricians in the room, they're going to say, this is easy. Why are we going through this? But remember, we talked about everyone becoming multi-resourceful, being able to see things in the boiler room or out there that you're not accustomed to, but to pick that up. So everybody has knowledge of the different trades. And that's what's going to help everyone go into the next step, which would be the foreman, right? The foreman would have to have knowledge of all the different trades in order to do his job effectively. So with that, when you guys asked for electrical, we figured we're going to talk on some basic electric theory, okay? I always like to start out with real simple, all right? Current flows through a copper wire, just like water would flow through a pipe. If I have to get more water down to the end of the line at a quicker rate, what do? I increase the size of the pipe, right? So we do the same thing with wire. If I have to get more power down to the end of the line, I have to increase the size of the wire. So current always flows through wire as water flows through a pipe, okay? I'm going to start drawing too, just to make you guys understand a little better. So we have our pipe, okay? This is at the end. Right now, water's not flowing through here, right? Because it's stopped. Say this valve is closed. In electrical, the terminology is just a little different. So when the valve is closed, water's not getting to the other side. When we open the valve, water will come through, right? In electric, it's just a little different. Comes down. When the circuit is open, current won't flow through the circuit. When we close that circuit, current will flow through the other side, okay? So it's a simple switching mechanism, all right? So that's the only difference when you're thinking about it. Close is open, open is close, all right? Imagine switches as valves. That's exactly what I just talked about, okay? A switch is just like a valve. When a switch is closed, current flows through. When the switch is open, current will not flow, all right? Power is equivalent to heat. The more power generated, the more heat that's going to come out of that circuit, okay? If you try and run power over a wire or a piece of copper that can't handle that amount of current, the wire is going to burn up, okay? Our welders in the room, arc welders, right? Arc welding is electric, right guys? And with that electric, we're melting wire. When we bring our electrode and ground together, what happens? It arcs. And it arcs at such a high heat that it melts that wire and brings two pieces of metal together. That's what we're doing when we're welding, right? It's heat, okay? So power is heat. How is power measured? Everyone has heard watts, right? When you look at your electric bill, it's measured in kilowatt hours. What does that mean? 1,000 watts per hour that you use, that's what you're being charged on, right? So power is always measured in wattage, okay? The larger the load, the larger the wire needed. Just like we talked about a pipe. More water down the end of the line, the bigger the pipe size, right? The more power, the larger the load on the other end of the line. If I have a 5,000 watt heater, as opposed to a 1,000 watt heater, 5,000 is bigger than 1,000, right? So I need a larger size wire to get that 5,000 watts down to the end of the line and run that circuit safely, okay? We're going to talk about parallel circuits and series circuits. Parallel circuits is real simple. When we get to the next slide, we're going to go over that. Series circuits we see all the time in the boiler room as well. Okay? Down at the bottom, power is equal to voltage times current. It's a simple mathematical equation. All right? So power, which is watts, is equal to volts times what's current? Amps. Current is measured in amps, amperes. Okay? If we have any two of these values, then we can find the other one. Just like in high school, right? So if I got a 5,000 watt heater and I'm sending 208 volts to it, who's got their calculator? 5,000 divided by 208. Can anybody tell me? Anybody? It's about 25 amps, just off the top of my head. Anybody got it? 24.303. Very good. Okay? On the other hand, if you have your voltage and your amps, we got a 110 volt circuit, right? Normal house current times 1 amp. How many watts do I have? How many watts do I have, guys? 110. Very good. 110 times 1 is 110. That's the amount of watts we're going through, okay? Parallel wiring. Right out of the circuit panel, if I bring one breaker and a fuse, when you see this, that means a fuse, all right? And I put 3 lights all in parallel. This is my neutral wire. This is my hot. Together, I get 110 volts. These 2 wires together, okay? Parallel circuit. If I put them all in line and I energize this, all these lights are going to light up, okay? Switch wiring, just like we showed on the board. When the switch is closed, the light lights up. When the switch is open, no current flows through to the light. Pretty plain and simple, right? When you see it that way? Any questions on that? This is what you guys see outside coming into the house. All right? So you have utility wiring at the pole. Comes in a loop to the house. Some of it's going to be underground. Some of it's going to be overhead. It's considered overhead service. And it feeds a panel, a service panel, into a main breaker. Feeds that panel. You have 2 hot legs coming in and a neutral. Between the 2 hot legs, you'll always get 220 volts, which is a generalized statement. Some areas is going to produce 240. Other areas are going to produce 208, depending upon where you are. Parts of Long Island is 240. In the city is going to be 208. From each one of those legs to neutral, you should have 110 volts. Okay? From any one of those legs to ground, you'll also get 110 volts. The reason why we have to ground our service or our system is because in a case of overcurrent or in a short, we want that electric to die in the ground and dissipate. Otherwise, it's just going to go through the whole system and start blowing stuff out.
What's the purpose?
Question?
Of the ground?
Purpose of the ground, exactly like I said. If something shorts out to ground, that electric has to dissipate into the ground. Otherwise, if there's no ground, that circuit is that short overcurrent is going to go through the whole system and start burning everything out. When you short something out in between neutral or into ground, right? It's an inrush of current. And that inrush of current, to protect everything else, remember, we said it's heat, right? Inrush of current is going to produce so much heat, that's what's going to start a fire. Okay? So that inrush of current, we want it to dissipate into the ground, which is your water main. In most cases, it's tied into a water main. A lot of times you'll see a ground rod driven into the ground. It has to go out into the ground. Okay? That's the main reason for ground. Neutral is not ground. Neutral is part of your circuit. Ground is your box, your ground wire, your conduit. Okay? It's protecting that system. And with that, we're going to go into the next step. It blows your fuse or activates your fuse or circuit breaker. Okay? A lot of times you'll look out and you'll say, wow, the transmission lines that go down the block, they're about that thick, right? How is it feeding this whole neighborhood? Remember we talked about power is equal to voltage times amps? The way they do that is before that transformer, those volts could be 10,000. So with 10,000 volts, I can get a lot more with a smaller wire, right? I can get a lot more amperage down the other end and produce and provide more electric. So as you increase your voltage, you're decreasing your amperage. Okay? That's on the primary side of the transformer. Secondary side of the transformer would always be down house current, which is 110, 240 volts. And then we're going to get into three-phase, which we see a lot of, but the voltage is still the same. Okay? Any questions on that? I don't want you guys climbing up the electric pole with a tester and trying to test it, see if Vinny's right. All right? Electric distribution. Everyone has one of these in their house, right? You'll see them in the boiler room as well. So the power comes into a main breaker. Reason why they call it a main breaker is exactly what it's doing. It's protecting this whole panel. So it's the main. We shut that off, it kills everything in here. Okay? The main breaker supplies the bus bars. You see the bus bars come out? Supplies the bus bars. And it'll distribute into the various breakers that you put in, whether they be single pole breakers, double pole breakers. We have GFCI breakers. You'll see them. Okay? This is our neutral bar, okay, which gets connected to ground, but it's not a ground. Okay? It just gets bonded to ground so that if there is a short to neutral, it goes into the ground. All right? This only happens at the main service. You don't join ground and neutral anywhere else after the main service, which means at this main breaker. Downstream of that main breaker, you never ever connect neutral and ground again. Okay? It's only at the service. Reason being is you can confuse that inrush. If it's connected somewhere else down the line, it's not going to know where to go. It's going to try and go there or go through the building to get to the other end where you might have grounded the neutral. Okay? So it could cause a problem. Yeah.
You have a three-phase service coming in.
Yeah.
You change the wire of the motor. You reverse the motor. How you have one pin on each line coming in. When you change the wire, how does it reverse the motor?
That's a good question. Did everybody hear that? Okay. We're talking about three-phase system, right? In a three-phase system, he's asking, when we change the rotation of the motor on a three-phase motor, how does it change the way the motor's turning just by switching two wires? We have three legs coming in. That's our three-phase. Okay? There's no neutral. On alternating current, you've heard AC, right? You'll only see three-phase in alternating current. You'll see single-phase 208 in alternating current. this is a single-phase alternating current panel. Direct current, other countries in the world, you won't see three-phase, okay? But in alternating current, you have a sine wave, okay? And this sine wave is the current alternating between your legs. Everybody heard the frequency at 60 cycles? If you see on a motor, it says 60 cycles. It's 60 cycles per second that it makes that sine, okay? So it alternates from A, B, C, if this is phase A, B, and C. It alternates from A, B, C, C, B, A, B, C, C, B, A, and it makes that rotation. If I change any of these two wires, what am I doing? I'm switching the rotation of this sine wave. Now it's going in the opposite direction, just by switching those two wires. So it's that alternating current, how it alternates from phase to phase, that produces your rotation, okay? Now, seeing that you brought that up, on a single phase, 208, this is neutral, that's A, and that's B. Single phase 208, because like we saw on a slide before, two phase legs, I'll get 208 in between the two. From either leg to neutral, I get 110 volts. It's the same sine wave, 60 cycles per second, okay? The neutral carries the imbalance or balances out the phase legs because it's part of that circuit, all right? That's alternating current. Megahertz would be the frequency on like a low voltage circuit. It's going to be a lot more than 60 cycles. It's like mega, it's like 1,000 hertz, right? So it times that. Okay? Any other questions on that? Choosing the proper overcurrent protection. What is overcurrent protection? Circuit breaker or a fuse, right? And what is its purpose? Exactly. If you buy a 15 amp breaker or you use a 15 amp breaker, it's not going to allow more than that 50 amps at a certain time. There's a time limit on that, to flow through that wire, and it's going to protect the wire downstream of it, right? So that someone doesn't try and pull 60 amps through a wire that's only rated for 15. Because what's going to happen? The wire is going to burn, right? Because power is heat. The more power, the more heat. Okay? That's the reason for an overcurrent protection. So you have different types of overcurrent protection. You have your main breaker, which is overcurrent protection for everything, which is the whole panel, okay? And then you have your individual breakers, which are your distribution for each individual line. And they're sized for what they're providing power to, right? Or what they're protecting is a better word for it. So if I have a range or a cooktop, obviously the wire is going to be a little bit thicker, and the amperage on that breaker is going to be larger, because a cooktop is a heating element, and it draws a lot more electric than a light fixture or a lamp, right? Or a small motor. Larger the motor, the larger the wiring too, right? Everyone get that? Okay. Different types of overcurrent protection. You have your single pole breakers, your double pole breakers and your 3-pole breakers. 3-pole breaker, where are we going to see that? On a 3-phase circuit, which is always going to be motors. Okay? A double pole breaker you're going to see on a 240 single-phase line. Single pole breaker will always be a 110-volt line. Okay? These are also types of breakers. You'll see them in the burner cabinets. They're little rocker switches, right? But they're run on one side. They're a mini breaker. A lot of times you'll see them. They're sized at 10 amps. They might be sized at 15 amps. All right? They're protecting everything downstream of them. And we're going to get down to how they work. This is the inside of a circuit breaker. See this electromagnet? That senses the heat when there's overcurrent, and it's sized for whatever the size that breaker is, right? So it senses the heat for overcurrent or for short current. Because in short current, it's going to inrush back, and it's going to heat up and trip. All right? All it is a lever mechanism with a snap catch. When this heats up, this breaks open, this flips off, and it breaks the power right here. You see that? All it is a switch, right? Just like we saw on a board. This is a closed circuit coming through and feeding the panel, feeding the wire. When this trips out, this opens right here. It's an open circuit. Kills the power downstream. All right, so all it is a protective device. Very important that it's sized properly. Because if we don't size it properly, the chances of that tripping are less, right? And if it doesn't trip and there's a problem, what happens? It could burn. All right, that's why everyone thinks about electric and they say, we're not touching it because it always starts fires or could start fires. Yes. If you size everything properly, if you do the work right, it's going to be safe. If you don't do it properly, then yes, it can cause fires. All right? That's the severity of it. Everyone get that? Okay. Yes, sir. Yeah. You're absolutely right. You're absolutely right. What he's saying is, if he has a main breaker, like we had in the panel, okay, this main breaker, and it's 100 amp rated, okay? And then this breaker is 50 amp rated. But there's a short downstream of that. Downstream of the 50 amp breaker. There are times that this breaker will trip before that and kill the whole panel. And electricians see that. It's called fuse coordination, okay? The breakers are rated at an inrush current value, okay? And you'll see them. It could be 10,000, it could be 20,000, it could be 30,000. When you purchase that breaker, you have to make sure that you coordinate them properly, that this one is a lower range than that. You understand? It's called fuse coordination. You'll see it on the fuses as well. And it's in the code now, too. It started in 2010, where you have to prove fuse coordination. Because a lot of people are just buying breakers. Now, on overcurrent or draw, this one is going to trip first. But on short, on dead short, that's where you're getting that breaker tripping first. Because on short current, it's going to trip, it's got a lower rating than that one. Okay? You look at the side of the breaker, it'll tell you what the short current ampacity is. All right?
In other words, you're saying one is a high range, one is a low range.
They're different rating of ampacity. of short current ampacity. Electricians will see it. Most of us won't even look at it, all right? It is no good. It's sized wrong. It's sized okay for overcurrent protection, but not for short current, okay? Overcurrent protection, we talked about fuses. This is a silver sand fuse, okay? Difference between circuit breakers and fuses. Anybody? Fuse is one time. That's it. It blows, it's done. You're throwing it out and you're getting another one. Circuit breaker is a resettable device, okay? Everyone has seen these, right? They're just screw shell socket fuses. And when it burns that link right in the center, right? Once it burns, what is it good for? Garbage. That's it. Throws out. Okay? How does the socket work? All it is a switch, basically. Right? The electric goes in here, comes out here. Just like a light bulb. It's a screw shell socket, okay? And the link makes the two. Once it's broken, the electric stops right there. These fuses here, there's a link inside there. All it is a small little wire that's rated at a certain amperage rating, depending upon what this is. This is a 400 amp fuse, all right? And it's filled with sand. Once it blows, everything comes apart inside that fuse, okay?
And that's operated by heat constant.
Right. Overcurrent or short current. The heat comes back and burns it off. That's why you see how this gets black. When the fuse breaks, it's black because the heat just melts off. Remember, we talked about welding, right? It's heat. Electric is heat. Okay? Yeah.
How come you can rip one live wire and not get hurt when it's hot when you touch the second one? You get hurt.
That's a good question. We're going to go back to our phases and our neutral. Okay? And what Danny's asking is, correct me if I'm wrong, if I touch A and neutral, I get a shock. If I touch B and neutral, I get a shock. If I touch A and B, I get a shock. If I touch just A, and I'm not grounded anywhere, not a completed circuit, right? Remember the sine wave? The alternating current? If you just touch A, and I'm not grounded, or I'm not touching neutral, I'm not part of that circuit yet. There's no voltage there. I need both A and neutral to get 110 volts. I need both A and B to get 220 volts. Or I need A and ground, because essentially neutral is a grounded conductor, right? So I need A and ground to get a shock, or the box, right? Or I need B and ground, which would be the box, or A and neutral. If I just touch A, there's no voltage there. It's not voltage on alternating current until I touch the other side or I touch the ground, okay? We've seen that too, right? When we clamp on welding machines, and the clamp comes between the two bus bars, what happens? Big black mark, right? Because we're crossing the phases. And it's just going to blow at you, okay? Never want to cross the phases. As soon as you cross phases, you have a dead short. And it's either going to blow the fuse and shut off, or if the fuse isn't fused properly, it's going to continue to burn and melt until it's done. All right? Until it breaks off or burns off. All right? Any other questions? Which ballast? You have to be grounded. You have to be grounded. Yeah. You have to be grounded. You're talking about at the sockets. If you touch the sockets and they're on, if you're touching from there to ground or the light fixture, you have to be grounded. You'll get a shock. If you're sweaty, right, salt in your body, the salt in your body will bring out that too. This is just so we can explain the wire size, okay? So this is United States wire gauge. See how we have number 12 wire? That's the gauge of the wire. The diameter in inches or millimeters is smaller than 11 or 10, right? So as the number gets smaller, the wire gets larger. Okay? So if we have 12 all the way to 1, number 1 is a larger wire than number 12. Number 12 wire is thinner than number 1 wire, okay? So what does that mean? What does that tell us? Between a number 1 or a number 12, what carries more current? Number 1, because it's bigger. 4/0 is almost a ½ inch in diameter. All right, so 4/0 as opposed to 1/0, which is smaller, it's like a third of an inch, right, in diameter, or 8.25 millimeters. It's smaller than the 4/0. The 4/0 obviously can carry more current safely than the 1/0, right? Pretty simple, right? Just like pipe sizes. I gave everyone a copy of this. All right, this is right out of the code book, and it tells you what size wire can safely carry what current. All right, and if you notice, it may be a little confusing because it's so large and there's different columns, but basically, the top of the column is telling you what's the insulation on that wire, okay? This column here is the thickness of the wire, or the gauge size. The insulation of that wire has an ampacity rating, okay? So THHN wire has a higher ampacity rating than RHW. THHN is thermoplastic, okay? Because remember, it's heat, right? So that insulation can withstand more heat than the rubber. Okay, that's why you'll see them higher in this column than in this column. Only difference is this wire can carry up to 90 degrees Celsius. This wire can only carry up to 75 degrees Celsius. The connection points where we connect our wires to, which is at the circuit breakers or on the panels, there's no connection point made at 90 degrees yet. They're only 75 degrees. So even if we use THHN wire, we still have to rate it at an RHW column because that connection point is only 75 degree rated. They don't make the lugs, they don't make the screws that are 90 degrees Celsius rated yet. All right? So this is the column we're looking at. The column here is saying, okay, number 12 wire can safely carry up to 25 amps. Okay? We fuse that at 20. A number 10 wire can safely carry up to 35 amps. We normally fuse a number 10 wire at 30 because you're not going to buy, it's very rare to find a 35 amp fuse or breaker. Okay? Number 8 wire is at 50 amps. We normally fuse them at 40, but you can carry 50 amps on a number 8 wire safely. All right? And so forth and so on. As the numbers get smaller here, the amperage rating gets higher. Then from here, when we get to 1/0 and higher, as the numbers increase, the amperage rating gets higher. Okay, so 1/0, 2/0, and 3/0, the 4/0 is bigger than the 1/0. This here, these numbers, they relate to circular mills, and that's the diameter of the pipe, the wire. All right, so this is saying this is 250,000 circular mills. It's just a measurement of that wire. Okay, the 500,000 circular mill is larger than the 250,000 circular mill. Okay, and so forth and so on. Any questions on that? Go ahead. I'm sorry?
Regarding the installation of the impactability rating, I think that's what we just said. Regarding the installation, the impactability rating, I think that's what we just said.
The rating of
Wire installation?
the insulation itself.
Yes.
Just like I said, the thermoplastic rating is higher than the rubber. It depends what the insulation that wire is. It can withstand or impact a lot more heat because it's a thermoplastic. It's like an insulator, right? So if you use R11 insulation in a wall as opposed to R22, which one has a better rating? The R22, right? Because it keeps more, it's got a bigger barrier. Same thing. All right, the thermoplastic has a better heat barrier than the rubber. Rubber's softer, all right? Exactly, and it'll heat up faster. Any questions on that? We looked at this before. We're going to hit it again. Light switch with multiple heights, all right? So our power source comes in, could be from a breaker, could be from an outlet. Our neutral goes straight through to the light, and the hot leg gets switched. When the switch is closed, power goes to the lights and lights the light, right? This is a parallel circuit. All it is in parallel with each other. Okay? Everybody get that? When the switch is open, current doesn't flow through that black wire. I need both the neutral and the hot in order to get 110 volts. If I open this, it's an open circuit, right? Will the light light? No, of course not. Just like Danny's theory, I'm not getting shocked. I don't have 110 volts there because this is open. Everybody get that?
How come years ago, when the wire switch, you just run the neutral to the switch, run the hot switch?
You're right. Years ago when they wired houses, they would switch to neutrals and not switch to hots. It was a bad practice. It was a very bad practice. And that's why they don't do that anymore, because it caused a lot of problems. They used to fuse the neutral at times. It's a very bad practice. This is another example of a 110 volt circuit. So the voltage at the light is 110 volts, or voltage at an outlet is 110 volts. Same thing, it's a light, right? You just plug a lamp in or plug a drill in, requires 110 volts. It's the same power source. Okay, so this is my power source coming from my panel, feeding the outlet with my neutral. Okay, when I plug something into it, I'm going to get 110 volts out of that receptacle. That also feeds a switch. Okay, neutral goes straight through to the light. When the switch is closed, sends power to the light. When the switch is open, doesn't send power to the light, but this is still energized, right? Because this is before the switch. Now, if I were to put the switch here, and I shut this switch, would that outlet be energized? No. I open the switch. It's all it's doing is breaking that wire. Now everybody's confused, right? Okay. We're going to look at this real simple. We see this all the time. All this is a wiring diagram from a simple Carlin burner. Okay? 120 volts to start the appliance. When 120 volts is sent to this relay, it energizes the relay, okay? Thermostat is made, then it goes through its ignition. Make sure that that's the CAD cell, right? That's the scanner. Looking for a flame. And it goes through its process to fire the burner, as long as everything is okay. But I need that 110 volts to turn this on, right? So what turns it on and off? Switches. Very good. Our electricians know this. Right? So 110 volts is going to fire that burner, as long as all the switches are made. These are all limits, right? One could be a pressure troll. One could be a smoke alarm. One could be a low water cutoff. Aquastat. Heat timer. If the pressure is below a certain level, this switch is going to be closed. If the burner's not smoking, this switch is going to be closed. If the boiler has the right amount of water in it, that switch is going to be closed. If I need more water temperature, or the aquastat is set at a certain temperature and I didn't make that yet, this switch will close. But what we're going to do is we're going to parallel it with the heat timer. The heat timer is going to make heat. The aquastat is going to make hot water. Right? So either the heat timer or the aquastat can fire the burner. If I open one, but I still need the other to satisfy, the burner's still going to fire, right? If I'm satisfied on both hot water and heat, burner shuts off. I need heat. I don't need hot water. But all of a sudden, the boiler runs out of water. The boiler shuts off. Johnny? Can you see this from back there, Johnny? Okay. I'm going to do this in red so you can see it a little better. Remember, we talked about switches, right? This is a switch. This is the heat timer. It's in parallel. Remember, we talked about parallel circuits, right? It's in parallel with the aquastat. So either the aquastat, if that closes, it'll fire the burner, even though I don't need heat. The aquastat is satisfied, but I need heat. This closes, fires the burner. Either or control can fire the burner. In a series circuit, all switches have to be made. In a parallel circuit, only one has to be made, because it's in parallel, right? Very important when you're doing burner wiring. All the limits, or the high limits, have to be in series. If you're wiring them in parallel, right? They're all in parallel. One could be a low water cutoff, smoke alarm, or pressure control. If any one of them are made, it's going to fire the burner. That's a mistake, right? Because now if I run out of low water, burner's still firing. Okay, the limits have to be in series. Everyone see that and understand it? Everyone understand the difference between a series circuit and a parallel circuit? Okay? Real simple. In series, everything has to be closed in order for it to get to the end. Parallel circuit, you only need one to close. Okay, so all of our limits, or our high limits, are always wired in series. Okay? Any questions on that?
That's why
Go ahead.
when you would jump a circuit in the boiler room, that's an operator boiler, you have to make sure it's shut down on the limit. Whether it's low water or pressure source, you have to verify that too.
That's why first time we fire a burner, what do? We exercise the limits. We exercise the low water cutoff. We drain the low water cutoff, make sure the water comes out of it, make sure the burner shuts off. Now I know it's wired in series. Okay? Everybody get that? Okay. Basic rules when using electric. Always use caution. All right? You're going to get hurt. You can get hurt. Okay? Your body's a nervous system, right? Nervous system is an electrical system. But it can't maintain house current. So what happens is when you get shocked, it overtakes your nervous system, but you can't move. All right? I've been there, I've done that. It hurts. Okay? Just be careful. Be very careful. Never assume a circuit is off or dead. Always test it first before you touch it. If you don't have a tester, go get one. All right? If you can't get one, ask somebody for it. If somebody says, yeah, don't worry, I checked it, it's off, check it again. Okay? Always test it first. Never assume that it's off or dead. Keep the workspace neat. I'm a stickler for this. All right? When you're working with open wiring, open panels, remember, we're with open panels all the time when we're working in a boiler room, right? Those are open, live buses. If you keep the area neat, there's less chance of somebody tripping and falling into the panel, getting hurt. There's less chances of, pipe being everywhere, wire being everywhere, hanging all over the place, short circuit, something hits that. All right, neat is always safer. Everyone will always tell you that. Nobody can ever deny that, okay? And when you keep the place a mess, it doesn't mean that you're working faster. Because now you got to be cautious of not to trip over everything on, below your feet. So neat is always safer and more productive. Always install equipment in a neat and professional manner. When you're dealing with electric, it has to be neat and clean. Because if it's a mess, you'll never be able to trace it. You'll never know what's live, what's dead. All right? And then you're going to get confused. If it's neat, straight, and simple, it's easier to trace. It's easier to troubleshoot. All right? Everyone get that? I mean, that's pretty simple, basic, right? Hector? Color coding. It's important. We try and maintain a color coding all the time, right? This way, the next guy that comes down the road doesn't have to follow everything down and trace or troubleshoot the wiring. It's easier to troubleshoot if everything is color coded properly. Use the proper tools and equipment. That's, that says it for itself, right? You want to use the proper tools. You're not going to use uninsulated lineman pliers, right? You're not going to use an uninsulated screwdriver in a panel, right? You're not going to use just like the end of a knife to lock down a screw, because if it shorts out, it's going to burn you. All right? Use the tools required. All right? Very important. Always insulate live parts. Sometimes guys will know that a wire is open or alive. They'll open the wire, leave it hang, but make sure that it doesn't swing, and they'll walk away from it in a minute and not leave it insulated. And then some guy's going to walk through with a piece of pipe, bam, because he's going to hit that live wire. We've all done it. It's not right. You got to insulate the live parts all the time. All right? Know what you're doing and why. It's always going to be easier if you understand it. Okay? If you don't completely understand it, don't do it. Because the repercussions can be greater than the reward. Right? A lot of guys will say, I could do that myself. I'm going to do it myself. And not bring somebody in that knows, because it might cost them a couple extra dollars. But then they do it wrong, and now it costs them 4 times as much to replace all their equipment because they burnt something out. And it could be a simple thing. So if you're not 100% confident, ask questions. Okay? Clean and neat is always equal to safe. Okay? Simple mathematical equation. Clean plus neat is equivalent to safe. Everybody get that? So which would you rather troubleshoot? We see them all the time. You go into these old buildings, and guy after guy just keeps coming in and adding on, right? Now you got to go trace why this transformer's not working, or which breaker is out here. Would you feel comfortable looking at that, or would you feel more comfortable looking at that? It's obvious, right? Neat and professional manner. Neat and professional manner. This is unprofessional. Potential for somebody to get hurt. Right? I just added that in. I thought it was cool. All right? That's Homer, right? You're working in the nuclear plant. All right. One other thing before I finish, though, because that was the end of my electrical basic. Any questions on that? Anything that we heard tonight? We're not all going to go home and start wiring our basements, right? If I can help you in any way, if you have any other questions, and you don't want to bring them up here, catch me on the side. You see me on a job site. Hey, Vinny, you were talking about overcurrent. What does that really mean? I want people to ask me questions. One thing before we go into break, because I got a few minutes. Yesterday, a question came up about smoke alarms. Saw breaching coming out of the boiler, right? We always put a nipple and a nipple. That's the exhaust. We put a piece of pipe across, and we hang smoke alarm and a receiver. One is a light. This is the receiver. What it does is it shoots the light through this breaching, right? And if the smoke breaks the beam of light, it tells somebody that the burner's smoking and shuts the boiler off. It's a requirement, right? On this light, you're going to see a chain. And a piece of plastic. When we go into the boiler rooms and we see that piece of plastic that still has the paper on it, the inspectors look at that and say, hey, the smoke alarm's not calibrated. How do you know? Because you never took the paper off the plastic. You need to take the paper off the plastic in order to properly calibrate the smoke alarm. Okay? All this is a piece of plexiglass, and it's smoked plexiglass, right? You might not see it, but it does have a tint to it. You take the paper off, you put it in front of the lens, and then you set the dial down till it rings. When you remove the lens, the light should go out. And then I want you to just move it a quarter turn back brighter. Quarter turn brighter, okay? So when the inspector comes in and says, you didn't properly calibrate the smoke alarm, he sees that paper on there, he knows why. And you can't debate it, all right? So on the smoke alarms, when we go in, take the paper off. Try it next time. Put it in front. See what it does. Lower down the intensity, you know, the little dial on the back of it. It's for all you electricians, all right? Just put the lens in front of it, lower the intensity of the light, wait for it to ring, drop the lens, see if it shuts off. Then just raise it up a quarter of a turn, okay? Make it a little bit brighter. Then when Alfred comes to service the burner, he's going to say, smoke alarm is too dim. And he's going to raise it up because he doesn't want to get called at 3 o'clock in the morning. That's fine. Let him do that. But we got to take the paper off, all right? Because the inspector's going to see that. Guys, anything?
Benny,
Yes, sir.
question to the
Yeah.
electrician, light running the light in the boiler room. Sometimes when they put the light in the back,
You're right. We've come across that a lot. The light fixtures, where they get mounted, if they get mounted close to that receiver, it can affect that smoke alarm. And from time to time, somebody leaves the boiler room, shuts the lights off, and then now the thing starts ringing. Because the light is affecting that smoke alarm. So it's very important. As soon as you set this smoke alarm, just like we talked about with the lens, next thing I want you to do is go at the entrance of the boiler room and shut the lights off. And then see if it rings. If it does ring, calibrate it with the lights off. Okay? Put the lens in, have somebody stand at the door, you go up there, you set it, let them turn the lights off, and then drop the lens. Okay? It's a very good point. We don't see that sometimes because we just shut the lights off and we leave. You get the call in the middle of the night and the boiler won't start because the lights aren't turned on.
good job.
Thank you. Guys, all right?